Hi, well, welcome everybody. I'd like to introduce Eric Beinhocker from the Oxford Institute of New Economic Thinking. He's a leader in modeling the whole economy in terms of like individual agents actually capturing it at a fine granularity, task that is, well, extremely difficult. Welcome, Eric.
Yeah, thanks very much, Greg, for having me, and thanks everyone who's joining in and streaming in as well. Pleasure to be here. Now, I have to warn you, I might be a little bit distracted during this talk because as we speak, England and Germany are playing in the first round of the European Championships. And I've got a screen up in the corner here where I'm sort of just checking the score as we go. Also, if you hear screaming in my household, that's my wife, who's a huge England fan. So just to let you know, that's going on in the background.
I'll add, my Swiss wife was very excited yesterday.
Yeah, well, that was an extraordinary game yesterday. Really something. So I gather from talking to Greg that many of you, have some familiarity with agent-based modeling, have been looking into it, thinking about it. I also gather you've had talks by my good friends and colleagues, Rob Axtell, Doan Farmer, and others. So I'm going to sort of just jump in with some thoughts on using ABMs to model economic systems and human social systems. I've got a few slides just to kind of get the conversation rolling. So I'll just go through those and then want to spend most of our time, hearing from you and, questions, discussion, hearing about what you guys are working on and so on. So I will go ahead and see if I can get these slides up. There we go. Share. And hopefully that's working now. Let me know if that's not coming through. So the first point that I want to make is that agent-based models aren't actually new in economics. Arguably, the first one was developed in 1971. Thomas Schelling, using, because he didn't have powerful computers in those days, he used pennies and a big grid that he drew by hand. Model the problem of segregation racial segregation in American neighborhoods. And he showed in this very simple agent-based model where each penny was a household and the grid was the neighborhood, a very interesting result that you could get very high emergent levels of segregation, even if people only had mild, in-group affinity for people like them. And what was interesting about the result was it didn't actually reflect the average or the preferences of the people, that people actually didn't really want to live in segregated neighborhoods, but just a little bit of this in-group affinity created actually quite highly segregated neighborhoods. So it was became a classic model and a classic example of emergence. And so that was a kind of, first agent-based model, albeit using without computers. Now, despite this long history, economics has historically modeled the economy using what people call methodological individualism, that instead of assuming, like in Schelling's model, that individual behavior can create emergent macro patterns that may be different than the individual behavior, traditional economic models basically just assume everything adds up in the economy, that there's a kind of linear adding up of individual behavior to create a kind of representative or average behavior at the collective level. And in contrast, agent-based models allow us to see truly emergent phenomena where we have networks and dynamics and nonlinearities creating collective behavior that isn't just seen in individual behavior. And the economy is full of examples of this kind of emergent behavior, from business cycles, financial crises, stock market booms and busts, inflation, economic inequality, carbon emissions. All of these things are emergent phenomena. And so, I and others would argue the only way you could actually really properly model those is through something like ABM, because you don't see them in this kind of linear adding up style of model. A second big problem with traditional economic approaches is the models assume that the system always reaches some equilibrium, some steady state. And some recent work my group has done, this was led by Doan Farmer and some of our students, actually has shown that that's actually literally impossible in the economy. That they did some computer simulations of basically the space of all possible games and explored those spaces and showed mathematically that you will only reach equilibrium in a very small subset of games with small numbers of players, simple rules, and simple strategies. So a game like tic-tac-toe, you can be pretty sure of reaching an equilibrium, but in games with more than a handful of players, even a modest level of complexity, and also when you have behaviorally realistic behavior, and particularly learning behavior, you never reach equilibrium. You get these dynamic cycles of behavior, and that's what the economy looks like. So in trying to model the economy with equilibrium methods, it's just a big mismatch between the tool and the phenomena that we're trying to model. So we can see lots of reasons why ABMs are needed in economics, that we can incorporate much more realistic agent behavior and things like learning, adaptation. We can also capture the full heterogeneity of agents, different households, different firms, different banks, and so on. We can also realistically model the institutional and network structure of how those agents interact, get the dynamics. We can also have endogenous system evolution and get the kind of emergent phenomena that we see in the economy. And that's very different from what we can get out of the traditional kind of structural equilibrium optimizing models most economists use. And also, we can take full advantage of the information that's in microdata. So in microdata on households or supply chains or financial data, there's a lot of information down at the granular level that gets lost when it's aggregated in the more traditional models. And you're really only limited by your computing power and your ability to just understand and manage your model, whereas in the traditional approach, you have very strict limits on what you can do just by the mathematical techniques themselves. And finally, these traditional structural models have kind of big garbage in, garbage out problems. Because the assumptions are so restrictive, the answers they produce are also very questionable. Again, the equilibrium assumption creates a strong status quo bias that, whatever the state the system was in before, was an optimal or equilibrium state that it will return to. And these models as such have a very poor empirical record. And just one example of that poor empirical record, here's a chart that the Bank of England produced looking at the results of their macroeconomic model. And their model, by the way, is considered one of the best of the bunch. Yet, as you can see, during the financial crisis in 2008, it performed very poorly on both its growth and inflation forecasts. And you can see how the model keeps pulling the forecast to some, previous equilibrium, some imaginary kind of full employment equilibrium, rather than being able to account for the actual dynamics going on in the economy. So, given all these advantages ABMs have, you could ask, why haven't they been widely adopted? They're still, not widely used in mainstream economics or in public policy. They're still kind of more of a research tool or used by, folks who come from a computing background. Now, historically, there were limits to computing power. Also, in creating ABMs, as you guys know, you have to figure out what the agents do, what are the behavioral assumptions, and people didn't have a good idea how to do that. These models are very data hungry. Is the data going to be available? Challenges modeling, these models are more complex. How do you manage them? Now, those, I would say those four problems, which have been historical problems, have actually largely, are being addressed. We have plenty of computing power. We now have a very rich set of data on behavioral assumptions that we can use in these models. You might be familiar with Josh Epstein's work on this. He wrote a very nice book on that called Agent Zero. You guys would know better than anybody what data is now available out there, and lots of great tools and approaches for managing the model complexity. Now, there's still four outstanding challenges. And that if you look at the ABM literature, most of the ABMs that have been built are really toy models. They may deliver some interesting insights, but they, they don't necessarily aren't calibrated as time series models, so they may not be that useful for actually testing scenarios, doing policy, making forecasts, etc. There's been relatively little out of sample testing of most models. And then I would say the biggest factor is just social factors in economics. Most economists just aren't familiar with these methods. Many of them don't necessarily have the computing or programming skills to build these kind of models. And it's just a very different approach from what most economists are trained in. Now, why does this matter? Well, the traditional economic models, the structural models, are embedded in lots of big important institutions, and many big decisions and policies are influenced by them, from how the Fed does monetary policy to fiscal policy that the Treasury or Congressional Budget Office might look at, to climate change policy. The IPCC models are very much based on this kind of traditional economic approach, and so on. So we're making some pretty big decisions in the policy world that are heavily influenced by what I would argue are essentially bad models, not very good models of how the real world works. So then the question is, can we do better? Can we create a new generation of policy models? And that is starting to happen. It's happening slowly, but step by step, we're making. We and others working on this are making progress. I'm not sure if Rob Haxtell talked about the housing market model that he and Doan Farmer built, but that model was adopted by the Bank of England, and some joint work we did with the Bank of England to build a very detailed model of the UK housing market to understand how housing bubbles form, and more importantly, what policies would be effective in minimizing housing bubbles that wouldn't have huge economic fallout, wouldn't have lots of side effects. And this was one of the first kind of true calibrated policy models to be developed that is actually fed into and been used in the policymaking process. And actually, this model resulted in some insights that were genuinely useful in preventing a new housing bubble developing in the UK. So, this is kind of an early example of what might be possible. And we like to think of these things like flight simulators, that this is a way of testing out lots and lots of different policies and looking at their impacts, without actually crashing the real economy. You just get to crash the simulated economy. Another example of a policy-oriented model that we've worked on is under COVID. One of the big questions was, how could we exit lockdown? This was work last year in a way that would maximize the benefits for the economy, but minimize the increase in spread of the virus. So how could we exit lockdown and keep the R0, the replication rate of the virus, below 1? And so we built a model, an agent-based model that had a model of the supply chain of the UK, and we linked that to an epidemiological model, and then used the two together to run policy scenarios on if we, open up manufacturing and construction. What happens if we open up retail shops and consumer businesses, if we open up schools, and so on, and looking at the joint effects on the economy and on the spread of the virus. And that helped find a sweet spot, where we could open up a significant amount of the economy and still help contain virus spread, at least temporarily, until new waves and variants came. And so this was provided as policy input. There's also, just potential in these models for better forecasting. As I mentioned, the forecasting performance of the traditional models has been very poor. And there's an increasing amount of work about how we could properly calibrate out of sample tests and so on agent-based models to provide a better forecast. This is a very recent paper produced by a group in Vienna that we're now actually re-implementing their model and expanding it and further developing it. Now, where might this kind of work lead? What might the vision look like? Well, you can think of, we have all this, a lot of rich data now on human behavior from the behavioral economics literature, from lab experiments, and also from, I'm sure, the kind of data you guys collect has lots of very valuable behavioral insights in it. We can also start to think about AI agents, and I'll talk about that a bit more in a minute. We can implement in these models, quite detailed portrayals of the institutions, the networks, rules of the game, how contracts work, how markets work, how information flows, portray physical geography. And, we can create detailed models of households, with incomes and balance sheets and lots of other demographic factors. I gather you had a presentation on Rob Axtell's firm model, which is also quite granular. Similarly, we and other groups have also done models of banking and financial networks. And then you can also portray government actions as policymakers. And then putting these things together, we can get new insights into these various macro phenomena in the economy. And we can then apply those insights in a variety of applications. Of course, for academics like me, this is an important research agenda, but there's clearly a number of important public policy applications for this. And then also in the private sector, I wouldn't say we've seen yet kind of a killer app for these types of models, but increasing interest from hedge funds, retail, e-commerce. Manufacturing and supply chains is a very interesting one because there's much more supply chain data available these days than there has been before, and also lots of concerns about supply chain robustness that have been revealed by COVID, for example. And then also the energy sector making the zero carbon transition. We've been doing some work on that. And I would also add insurance is another area where we've been applying ABMs. So we're working toward a vision of building what we think of as a kind of ABM Lego set, where we have a set of modules and models that we can link and unlink, and they can play with each other in different ways. So at the heart of this is a kind of input-output model of the economy, basically not just the supply chains, but kind of the whole input-output structure to look at macro issues and growth issues, and then a labor market module that looks at occupations and jobs. Also a household module that looks at household balance sheets and income statements. And then various kind of more applied pieces, for example, a model of the energy system to look at for issues of climate change and so on. Also a capital markets module looking at banking networks, financial stability and risk and things like that. And then these things can, hopefully be linked together in interesting ways to work on different problems. Now, lastly, just like to mention that there's also some interesting, potential to marry up ABM techniques with AI and machine learning techniques, and we have a few folks in our shop who are doing some work on this. So if we think of, the traditional AI ML model, of sampling a complex space with data and then, having the algorithm learn from the data. Another approach, which your colleagues at DeepMind have used, is learning games, where you explore a complex space by agents basically playing the game with each other, such as the AlphaGo Zero AI. And you can see that ABMs could be something that could marry these approaches up, where you have a micropopulation of heterogeneous adaptive agents. You then have a kind of a mesospace, a strategy space of whatever the game is, and the payoffs. And that strategy space and the payoffs are evolving as the agents play. And then you get the emergent macro behaviors. So you have agents both playing the game and creating the rules of the game as they play. And that's essentially what humans do with the economy. We're both kind of playing the economic game and we're making up and changing the rules as we go. And that raises some interesting questions, and I think your colleagues at DeepMind have done some very interesting research on this, of if we create a simulated worlds of the economy, could AIs learn how to play the economic game better? Could they come up with better policies, better approaches than we might otherwise think of? But also, can they come up with innovations in the rules of the game, of how we can change the structures of the economy in ways that deliver better performance for whatever our objectives are, whether it's going to a zero carbon economy or greater economic opportunity for people or what have you. So I think there's some very exciting unexplored or yet to be explored spaces using these technologies. So that hopefully just gets a few thoughts on the table, and glad to open it up for for discussion and questions. And again, would love to also just hear a bit about some of the things you guys are thinking about and working on.
So obviously I have a bunch of questions, but what do the folks here think on the call? So then let me start. The biggest challenge for ABMs is their complexity. So it's fairly easy to create a model of whatever you think the world is. What challenges and opportunities do you see in using real world data? In fact, I didn't see that Vienna paper, because maybe you can discuss that, to tune the parameters of a model that may have a ton of them, right, for all the agents.
Yeah. So as we were talking, Greg, for a few minutes before the call, sometimes you're in a position where you kind of know what the structure of the world is, and you want to reflect that in the model. So, in the case of like the UK housing market, we may know things that, if you're buying a house, you go through a process where you go to a realtor and you look at some houses, and then you put in a bid, and other people put in a bid, and you kind of got this market structure that you then try to portray in the model. Now, how do you parameterize that structure? Well, then you may go to the data and kind of pull that out of the data. Other times you may not really know what the structure is, and so you may then just take a purely empirical approach. And we've created ABMs where there's sort of little econometric models that are sort of attached to the ABM that are handling certain tasks, because we just don't know what the underlying structure is. Now that has limitations, because the econometric models, if there's a structural break in the data, then that may invalidate the econometric model. Although one of our colleagues, David Hendry, does a lot of work on using machine learning techniques with econometric models to be able to handle those kind of structural breaks better. Now we haven't gone the step of trying to integrate that in with ABMs yet. But it's a hard problem. But again, the question is, these techniques are never going to aren't going to be perfect, but are they better than your alternatives? And most of the alternatives, at least that we have in economics, are have even bigger problems.
Well, let's compare. So I'm thinking the NIGEM, that's part of the Bank of England model, essentially. Yeah. That one, every term in there is an observable data set, right? They're very coarse terms. It's like unemployment rate. That's as granular as they get. But at least there's a data set for it. Whereas in the database model, you usually have a bunch of things like people's preferences, and they're never observed. And so when you have real estate, thankfully you have every single transaction. But I think the validation you were mentioning before was GDP. All you have is this highly aggregated data set. How can you possibly infer what the underlying agents are doing?
Yeah, well, the answer is you can't. Not from that kind of aggregate data, particularly with very limited observations. Most economic data, you have 40 years by quarter. So you've got 100 and you've got a very limited number of observations. But what you can do, and this is, what I assume Rob Axtell showed you with his firm model, is, you can kind of build from the bottom up, and then, calibrate against the, against the aggregate data. And, now, again, you could be getting good results for spurious reasons doing that too.
Oh, yeah.
But, it's a bigger hint you're on the right track than, again, when you compare it with the, the standard like DSGE models and so on, which are just giving you, have nonsense structure, nonsense behavior, and nonsense results.
Yeah.
You're still, probably a bit more confident. But these issues of calibration are among the hardest that we face. And I think that's one reason why there are so few kind of calibrated time series models out there using ABM techniques. Have you guys found any good approaches for this stuff?
So then maybe let's start from the bottom up, because that's kind of where we've seen most promise. I mean, there's some folks on this call do a power grid modeling, and their agents are sort of sane. They're mostly inanimate. And so there's a promise. In fact, I think most of the power grid models are effectively agent based, except they're fairly predictable agents. Supply chains are a very obvious one. If you know the shipments of individual goods, and the examples we've heard were warehouses in this part of the country are slower because of unions, or because it's a sports game day. So on those days, that better be part of your data set. You can learn that on holidays or whatever, these warehouses are slower because they deviate in insane ways. Some things go too far, like mobility. People do model how people travel individually. Google uses such data to predict your travel. But beyond that, they've really run into the wall of privacy. And that's where I think the wall has been. In fact, let me ask you about one particular wall, initial conditions. Even if you get the model perfectly right, you're never going to get the time series exactly the same as the true time series, or at least it's very, very difficult. And that seems to be true for everybody. I think equilibrium models get away with it by being so coarse, so they don't predict all that much detail. What's a promise there? Because I'm not seeing very good validation techniques that adjust for the fact that initial conditions are always going to be imprecise. Yeah.
Well, so I would answer that by asking what you're using the model for. So if you're using it for forecasting, beyond the relatively short term, it's a big problem, because any nonlinear dynamics will kind of explode, pretty quickly. If you're doing a kind of more of a sort of short-term forecasting learning approach, where the models, continually updating and stuff.
Like weather models, actually, that seems reasonable.
Yeah, you can, again, you're probably beating the competition,
right?
Even though you're still, and again, it depends on the application. In some cases, you might be good enough to be useful. In other cases, not. Just like the evolution of weather forecasting, which faces a similar similar set of issues. And again, in weather forecasting, a combination of better data, better structural models, it's allowed the kind of useful forecast length to grow over time, even though, it's still limited. On the other hand, where I'm more, where I think it's easier to, to be optimistic are these kind of scenario game playing models, so the housing market model I showed, can we predict another housing bubble in the UK? Probably not. Now, can we give warning signs that one might be emerging? Yes, and that's useful. Also, can we also simulate lots of policy responses to bubbles and find that, some policy responses are likely to either be ineffective or create a lot of collateral damage, like just jacking up interest rates broadly, has huge collateral damage. Whereas, what this model showed was some very specific policies on bank credit policies could be quite effective with minimal side effects. again, for a policymaker, that's quite a useful insight. And then then you go to the real world and you try it. And
Right.
in this case, the Bank of England did try it. Now, we won't claim it was just because of this model. It was, like any policy process, they're not just listening to models. There's lots of data and debates and things. But anyway,
Of course, yeah.
they tried a different approach than they had in the past, and it worked really well. It was the famous Sherlock Holmes, the dog that didn't bark.
Right.
The potential for a housing bubble was there. It started to come up, and they kind of nipped it in the bud.
That's a good point. And then how, I understand the theoretical reasons to prefer this over equilibrium models. I mean, long term, I can definitely see how it'll work out. But a lot of their arguments for existence is, pretty much the same. It's how they're supposed to be used. Their validation problems are equally, well, maybe less severe because they predict less. So how would you compare for a given scenario whether an ABM or an equilibrium model is more likely to get the right answer or informative answer?
Well, the time when you actually really need models is when things are changing.
Yeah.
And when you're out of equilibrium, like the 2008 financial crash or COVID, or the transition to a zero carbon economy. And an equilibrium model is just not going to be that useful because it's telling you that the past was somehow optimal and will be gravitating toward that, or it sort of can't take into account the dynamics of change. So if we're comparing the two models, in a relatively kind of calm, steady state economy over a relatively short period of time, they might perform similarly. But I think these types of models, when you're trying to model any kind of major change, the ABMs are just more likely to be useful.
So maybe let's define what an ABM is. At what point is it just, we know that equilibrium models are a lie. The designers of those models know that exactly what kind of approximation they're making. So to what extent is it just saying that I'm going to start removing approximations and not have one agent per human, but simply say that it's not the banking sector. It's the big banks versus medium banks versus the small banks. 3 agents as opposed to 1 agent. And to what extent is it incremental decomposition taken to its logical extent? And if so, why not take one of the intermediate decomposition points as being good enough?
Yeah, well, no, it's a perfectly reasonable question. And again, the famous economist's answer, it depends. Rob Extel has done some interesting experiments with this firm model of, do you have to go to the full one-to-one, ratio? Do you get different results, or if you aggregate up to different levels? And for example, with banks, we know there's actually quite a number of dimensions of heterogeneity that matter. And this, we've discovered this both through data and through this kind of modeling, where just having big, medium, or small will actually miss a whole lot of the factors that contribute to financial sector risk. So, a key example is, you've probably heard the phrase, it wasn't too big to fail, it was too connected to fail.
Right.
That was the key. That was the key factor behind the Lehman Brothers collapse. And so, the models that have been most successful in modeling that kind of phenomena are agent-based models that explicitly model the network structure, have the balance sheets of all the banks, kind of are able to trace, what assets are flying back and forth between the banks. And in fact, there's a very neat paper using something like Google PageRank to actually understand the centrality in the network of those banks and which banks are too connected to fail, and then assess their risk in a different way than the traditional methods. And you'll never see that from a model, with either just one aggregate financial sector or just big, medium, small banks. For that, you have to get down to individual banks and their balance sheets and their network connections.
So trying to capture what a lot of the smells like the discussion you're saying right now is a lot of causal inference stuff, where you say that I can predict the outcome of this intervention because I need these covariates to make that prediction. And once you nail them, the covariates out of like the 1,000 you may collect, you find the 10 that actually are predictive. That's what you put in your model, and effectively, it seems like every causal study is the derivative of the model at one point in time. I mean, is that our way of getting an ABM?
Yeah, well, yeah. So I mean, ABMs are, causal models, and that, you push on one thing and there's an effect, and it pushes and it, bounces around the model. Now, again, they're not, they're not linear. You can get nonlinear, dynamics and causal cycles through them, and you can also bring randomness into the models as you need to, and things like that. So I mean, somebody who's mathematically a lot smarter than me might be able to say or show that there's equivalence across these different modeling techniques. But again, it's what are you trying to do with them? Because one of the things I've always liked about ABMs, and particularly in working on policy problems or on business problems, is I can look in our housing market, and I can say in our housing model and say this is a house,
right?
And it's got a set of attributes to it. This is how the market works. This is the house buyer or renter. This is how they make their decision. So there's kind of more of a mapping to our ontology of the world and the ontology of the model, than kind of more than other methods, which now ABMs can become black boxes too, because they can just get super complex, and that's a problem as well.
That's where I would ask, how do you know those are in any way related to real households? I'm actually thinking in physics models, they have a bunch of approximations where they, in various variables may be called whatever, but there's no guarantee that the values learned for those variables are anything close to what they are intended to be.
Yeah, well, so one of the things that our group does to often test these things is kind of understanding the state spaces of the model, and just creating some, in very rough ways, can the model go to places that the real world goes to, where the places it kind of can't go to, doing parameter sweeps and things like that. So you kind of, so the models aren't kind of completely uncontained, if you know what I mean. You can get some decent understanding of their behavior and how that relates to the real world. Now, you of course can have problems where some behavior that you thought, some weird assumption you're making about agent behavior, some structure is driving a lot of the results, and hopefully you pick that up in your testing and so on.
Debugging, essentially.
Yeah, there's a lot of debugging, and actually the kind of art and science of ABM debugging is getting better, but it's still still has some ways to go.
So then a good question at this point would be, what's the role of behavioral economics? Because they should be able to constrain what's possible.
Yeah, no, exactly. So one of the things, when I talk to economists rather than computer scientists about ABMs, economists always say, if you're not constrained by kind of rational behavior, you're in, there's a famous phrase, Tom Sargent, Nobel Prize, used the wilderness of irrationality, that kind of anything's possible. But we know from, and it's not just behavioral economics, but a lot of psychology, social psychology, cognitive science research, that humans do behave in a lot of circumstances quite heuristically. And, we can kind of back out those heuristics from the data, and, use things like laboratory experiments to validate some of that. And we've had some success with these heuristic switching models. So there's a guy at University of Amsterdam, Cars Holmes, who's done some lovely lab experiments, again, sort of backing out people's decision-making heuristics in different circumstances and games. And he's found that people will tend to apply a heuristic, and as long as it's kind of working for them, we'll go with that. And then if it stops working for them, then they'll reach into their tool bag of heuristics and pull out another one and try that one, for a while. And that heuristic switching creates, in a population, can create some quite complex, dynamics. And, we can actually see that, something like that in the data. And then in building the models, we try to replicate that heuristic switching dynamic. Now, again, we might program in a toolkit of 7 heuristics, and in the real world, there might be, 50. But the question is, are we kind of capturing the really key ones that are driving the macro dynamics of the system? So, again, there's probably just as much art as science, and plenty of limitations, and you always have to be, have a healthy dose of skepticism on these models. But again, that's still streets ahead of just having, a single rational agent making all the decisions.
I just noticed that Garrett had a question. Maybe, it's actually worth coming back to what the right granularity is.
I think we did address this, but maybe I can put a different question in. Yeah. So when we talk about the sort of promise of these approaches for modeling human systems, I find that like the reality, I mean, you just said this, right? But the reality is so far away from that. And ultimately it boils down to like a few parameters, more or less, in most of the applications that I see. And so I just want to understand, like, how do we go from here to there? And so you mentioned that like some people do behavioral experiments where they set up these like really careful situations, and then you can figure out like what type of decisions would be like in this exact situation under these exact circumstances. And it doesn't seem like there's a lot of space for generalization to a general human agent that is making decisions in a way that could actually be leveraged in a model like this at scale to sort of start to bridge the gap, to like actually realize the potential that we hear about in these things. And so I'm curious if you could just talk about like what that future looks like, or like what are the even steps. I mean, I could see a hypothetical world where you have to design games that recreate all of these situations so that we can train models that are good enough to do essentially what a human will do. I found it interesting that you said that the list of heuristics is 50. I mean, as a cognitive scientist, I might say that list is literally infinite in size, right? And so those are sort of some of the constraints that I come across when thinking about, like, essentially as a cognitive scientist, I would start from the bottom and just say, okay, we need to get human behavior encoded in a way that we could actually train these models to look like that. And that seems like it could be just complete folly in the sense that how much of that you would have to do to build a good model. But yeah, just curious to hear your thought. From here to there is the most concrete way I could describe this question.
No, great questions, Garrett. And well, first of all, it's terrific that cognitive scientists is engaged in this, because the field needs people with that background of working on these issues. And on the one hand, you're right. I mean, what's the heuristic to decide what I chose for lunch today? I mean, who knows? And is it even a reasonable question to try to back that out of some data about my past lunch history or what have you? But when we look at many of these systems, you often find that there's a kind of interplay between a small handful of heuristics that can explain a lot of the dynamics. So something as complicated as the stock market, there's again an infinite number of strategies people are following in the stock market, but a lot of the dynamics are explained by the relative weight of trend following strategies versus kind of more regressing to the mean fundamental strategies. Now, there's lots of flavors of trend following and regressing to the mean and so on. And in fact, my colleague Doug Farmer has just written a very nice paper on this, on what he calls the market ecology. But you can sort of often boil these things down, to some key behaviors and heuristics that are driving the macro system dynamics. I'm sure that's not true for everything, but for things from stock market behavior to another one actually supply chain volatility. There's again some relatively simple behaviors that seem to explain a lot of that. And in the COVID modeling we did, we found a few things like that. So I'm a bit more optimistic. So if you're asking, can we model the world in kind of one-to-one realism? No, the world's too complicated for that. And as the old saying goes, a map that's one-to-one scale isn't very useful because you can't fit it in the glove box of your car. Well, in the old days when we used to have paper maps before Google Maps. Can we create simplifications and models that give us insights we can act on in useful ways? I'm a bit more optimistic about that.
And something where I think maybe connecting it to like a learning approach. One thing I've been hoping for, honestly, is, so I'm going to refer to a particular model, which is like shopping model. And there's a few like models that like Suneti had an earlier one for people going to restaurants. I think the lead author is now DeepMind. Where the idea was you hypothesize, that you hallucinate, it's effectively a model of how a person shops. And the ultimate data set is what items they bought. But the process you assume is going to be, there's a hidden vector of their preferences, there's a vector for every item of their attributes, and you take a dot product and you just rank them according to the dot products, how much you like them, and just shop them in order, and finally you shop the exit item and you move on. And they have to add a few things, like if you buy, there's a bunch of complementary items, you learn what's complementary, like hot dogs and hot dog buns. If you get hot dog buns become more valuable. And then other things like tacos become less valuable because you're committed to hot dogs. So that's the process they hallucinated. And the thing is, if you have enough of a training set of actual shopping baskets, you will find a set of parameters for the damn thing that is pretty decent. So you have a prior of how you think the world is working, and it's wrong. But if it's rich enough that the parameters, the data is granular enough, and the solution is near this model, you get something sane. Yeah, no, and I think there's a lot of potential for using those kind of techniques in certain applications. Now, you have a problem. Where it gets hard is when agents are interacting with each other. So if you've got a kind of lone individual going into the shop, and or you have a population of individuals and they're each kind of going into the shop and buying some stuff, and you're trying to use the data to back out what they're doing. People are regular enough in their behaviors, you might have some hope of doing that again in a good enough way. But when you have these ecologies of strategies, where I'm playing, we're playing a game and I'm using one strategy, you're using another, but then I'm learning and adapting because my strategy works for a while and then it works less, and then I do the heuristic switching and I change strategies. Then it's a lot harder to kind of back it out of some data set. I mean, you have lots of clever people, so maybe somebody can figure out how to do that. But again, that's where we've kind of found, jumping back and forth between the lab and the model and the real world data, may help you kind of zero in on what's going on, because you can get people actually playing against each other, in something like a lab setting. Now, maybe a next step is doing the kind of stuff DeepMind does, where you have AI agents playing against each other and exploring the space of all these, exploring the ecology of strategies, and then seeing what that produces. That could be a very interesting approach. So that makes sense. Let me actually push you on the training side. So there's reason to be skeptical about the validity of those agents because you don't know what they are. But the really nice thing about that is that there are many. One arguably flaw of machine learning, as this actually practiced, is that it's you train a model on a consistent data set. You can have as much data as you want, but it better be a giant table of something, right? And lab experiments, as one example, do not fit into that. There are a bunch of heterogeneous things that came from different conditions, and talk about little sub agents, and they certainly don't fit into the one big table. One thing the ABMs have a promise for is saying that here's some agents. I'm going to train them from this lab experiment. And this other agents, bank, well, I have a specific data set on just banks. And if I toss various points of validation. You can imagine like a neural net with many predictions. It's making like side predictions for individual agents. You can validate against extraneous, very heterogeneous data. And that becomes possible because you have names for a bunch of objects in the world for which there are very different data sets. So has anybody tried that actually?
Not that I'm aware of. I think that's pretty next level to the kind of what I've seen, but it doesn't sound crazy. It doesn't sound impossible. I mean, it would take a real collaboration between obviously people with the lab skill sets, the ML and data side, and so on. But I think these are exactly the kinds of questions we need to ask and need to explore.
And let me just then poke on the causal inference studies, because that's another data set where it seems like they're finding these sharp gradients that says the world changed because tax policy changed, or like regression discontinuity, where some people are on one side of the test result versus the other side. And that seems like an unusually sharp training set to feed into a model saying, you better reproduce this discontinuity in your dynamics. What opportunities do you see there?
Yeah, well, so there actually, you guys might want to take a look at the work my colleague David Hendry has been doing. So he's he's a leading econometrician, but he's had a group for a while that's been modeling structural breaks. So something changed structurally in the world to shift the data. So first of all, can you detect structural breaks in the data? That's a big problem in itself, and they kind of solved that actually in a pretty rigorous way. And then then can you model the structural breaks? And they've made some really good progress with that now. And even though their methods come out of an econometric tradition, I think most machine learning types would kind of recognize them pretty quickly. Now, where I think there's some interesting potential that can you integrate those kind of methods with with ABMs in some interesting ways. Now that's a question I've been asking my team, because I've got Doan Farmer sitting in one office and David Henry in another. I was like, can you guys figure out how to do something together? But so I could see potential for doing something like that.
So maybe like in the last few minutes, if you were to do like a big collaboration, because I mean, that's part of the motivation for you speaking here, figuring out how these techniques can be pushed along and used by us in some ways, what would be the right combination of skills and technologies and that sort of thing? Yeah,
well, I think, so there's kind of two angles to, what we're doing, and we'd love to have, collaboration on. So one is just kind of building this, what, we call sort of the Lego set, this sort of, pieces of models that can be, used and reused in different ways. So, I'd love to build like a great model of US households, with really good granular micro data on household balance sheets and incomes and demographics and employment status and, geography and blah, blah, blah. And that would just be hugely useful for all kinds of applications. And then similar things about, firms and banks and so on. And then there's an angle of some killer problems to work on, where we know that the traditional models just don't give sensible answers and aren't very useful, whether it's for policymakers or for commercial purposes. And, so for example, we've got, I think, climate change transition to zero energy economy is, a big area where that's true. And so we've got various efforts on that. But, there's plenty of others too: supply chain robustness, financial market issues, et cetera. So I think you can kind of come at it from, both kind of building the tools and toolkit side, or come at it from, tackling some problems side. Now, one of the struggles that academia has had on all this is it does take a very multidisciplinary approach. So you need people who know how to do this kind of modeling. You need good software engineering. One problem with a lot of academic models, guys have probably looked at them or tried to recode them, as some graduate student was hacking their way in Python or whatever, and it's great for their thesis, but not much else.
Right.
You also need data resources, which academics often struggle to get access to. And then you need the other disciplines, cognitive scientists, psychologists, experimental people, and so on. And, you also need some people who do know a thing or two about the economy and economics. And so, the academic world has struggled to kind of bring all those pieces together.
That makes a lot of sense. And that's something we might be able to connect on. Thank you very much, Eric.
It's a pleasure.